Every battery fire begins with the same physical chain liquid electrolyte vaporization, temperatures exceeding 200 to 300 degrees Celsius, and an internal short circuit that triggers thermal runaway. Today's automakers attempt to control this chain through software limits and cooling systems. Donut Lab claims to break it at the material level. If this is true, this is not a battery that is merely harder to ignite, but one designed to have nothing inside that can burn in the first place. Let's examine the reality behind the safety of this battery. Start with the most direct contributor to battery fires, the electrolyte itself. Modern LFP cells still rely on organic liquid electrolytes, typically carbonate-based solvents such as ethylene carbonate and dimethyl carbonate. These materials have flash points in the range of 20 degrees Celsius to 30 degrees Celsius. Once internal temperatures exceed roughly 120 degrees Celsius due to abuse or internal failure, the electrolyte begins to vaporize and can ignite if oxygen is present. This behavior has been confirmed repeatedly in UL and NREL abuse tests, where even LFP cells, despite their reputation for safety, can sustain flames exceeding 600 degrees Celsius once the electrolyte ignites. LFP's advantage is real, but it is often misunderstood. The iron phosphate cathode does not release oxygen during decomposition, which significantly reduces fire intensity and slows propagation. However, the electrolyte remains flammable. LFP does not eliminate combustion. It merely limits how violently it unfolds. So the first uncomfortable question is simple. If the fuel for a fire still exists inside the cell, can we really call it fireproof? Donut Lab approaches this problem from a different angle. By eliminating liquid electrolyte entirely and replacing it with a solid electrolyte, the primary fuel source for combustion is removed. A solid electrolyte does not boil, does not vaporize, and does not form flammable gas mixtures. In thermal abuse tests conducted by several solid-state developers, including Toyota-backed programs, cells heated beyond 300 degrees Celsius showed mechanical failure without sustained flames. When there is nothing to burn, failure becomes structural rather than incendiary. But ignition alone is not the whole story. The second failure mode is thermal runaway propagation. In LFP cells, thermal runaway typically begins around 210 degrees Celsius to 230 degrees Celsius, noticeably higher than high-nickel chemistries that can enter runaway near 150 degrees Celsius. More importantly, the total heat release is lower. Published test data shows LFP cells releasing approximately 90 to 120 kilojoules per amp-hour during runaway, compared to over 200 kilojoules per amp-hour for nickel-rich cells. This is why LFP packs often self-extinguish if neighboring cells are adequately isolated. However, reduced does not mean eliminated. Thermal propagation in LFP packs still occurs under certain conditions. Tesla's own internal testing, disclosed through regulatory safety documentation, shows that tightly packed LFP modules can propagate runaway if heat flux exceeds roughly 15 to 20 kilowatts per square meter. Poor cooling, insufficient spacing, or delayed fault detection can still allow cascading failures. This raises an important question: if thermal runaway is merely harder to trigger, is that fundamentally different from making it impossible? Donut Lab claims its cell architecture breaks this chain entirely. If a cell fails but does not release large amounts of heat rapidly, there is no energy source to trigger neighboring cells. The failure remains localized. From an engineering perspective, this is not mitigation, it is prevention. The third claim targets a quieter but equally dangerous mechanism: metallic dendrites. Dendrites form when lithium deposits unevenly during repeated charging, eventually piercing the separator and creating internal short circuits. While LFP cells typically use graphite anodes rather than lithium metal, lithium plating can still occur during fast charging, especially at low temperatures below 10 degrees Celsius. Field data from EV fleets shows that a significant share of battery fires occur without immediate external abuse, pointing to latent internal shorts as a root cause. A 2022 analysis of over 10,000 EV battery incidents found that more than 30% of fires were delayed events, occurring long after manufacturing or charging. LFP reduces this risk through lower operating voltage and more stable electrochemistry, but it does not eliminate it. Donut Lab's solid electrolyte acts as a physical barrier to dendrite penetration, Laboratory tests of solid-state systems show dendrite suppression at current densities up to 5 to 10 milliamperes per square centimeter, far beyond normal EV operating conditions. If dendrites cannot physically cross the electrolyte, spontaneous internal shorts become far less likely. This leads to another uncomfortable but necessary question: if an internal short cannot form, what exactly is left to trigger a fire? Despite these advantages, engineering judgment demands restraint. LFP's greatest strength is not theoretical safety, but real-world validation. As of 2024, over 40% of global EVs use LFP packs, representing billions of kilometers of accumulated driving data. Failure modes are well understood, manufacturing tolerances are forgiving, and safety systems are mature. Fire incidents per vehicle are already statistically lower than internal combustion cars. Donut Labs battery, by contrast, has limited field exposure. Laboratory superiority does not automatically guarantee robustness at scale, where microscopic defects and process variation dominate outcomes. The difference between these two approaches is philosophical. LFP manages risk through chemistry stability and system-level controls. Donut Lab attempts to remove risk at the material level. One reduces consequences, the other reduces probability. Neither approach is inherently superior without context. For mass-market vehicles, cost, scalability, and defect tolerance matter as much as absolute safety. For aviation, robotics, or dense urban applications, even a single ignition event may be unacceptable. So the real debate is not about hype or allegiance. It is about where each safety philosophy makes sense. If LFP already survives nail penetration tests with delayed or no ignition, is the additional safety margin of solid-state worth the complexity? Conversely, if solid-state batteries truly cannot burn, will future regulations quietly make them mandatory in certain use cases? From the perspective of someone who has watched electrical systems fail in the real world, not on slides, the conclusion is straightforward. Donut Lab addresses the root causes of battery fires at a fundamental level. LFP remains the most proven and economically viable safety-focused chemistry today. One minimizes damage. The other aims to eliminate the event entirely. And perhaps the final question worth asking is this: if batteries stop burning altogether, does safety stop being a feature and start becoming an assumption?